Welcome everybody to the Asia Pacific Analysis and PDE seminar. It's really a great pleasure to see so many people. So I should apologize Enrico Valdinoci, who is currently traveling, and he asked me to chair this session today. And we have the great pleasure that we have Jack Thompson speaking today. He's a PhD student of Enrico, and he's working currently on a very hot topic of non-local PDEs. So he will speak on an overdetermined problem involving the fractional Laplacian. Jack, please start.
Okay, thank you for the introduction, Daniel, and thank you to the organizers for inviting me to talk in this seminar. So as Daniel said, what I'm going to be talking about today is this overdetermined problem involving the fractional Laplacian. So the idea of overdetermined problems is it's a type of equation in partial differential equations, and we essentially have a well-posed problem, and we have an extra condition which we call the overdetermined condition. Okay, and in general, this overdetermined condition, not every solution to my well-posed problem will also satisfy this overdetermined condition. So really the idea of overdetermined problems is not so much to care about the function, but to care about the regions that admit solutions to both the well-posed problem and the overdetermined condition. So this is really related to, it has very close connections to shape optimization, for example. And these kind of problems arise naturally in many different physical phenomena. So really, the first example, or the sort of the original overdetermined problems, kind of arose from this question here. So why are pipes cylindrical? Which is a little bit of a silly question, but if we just explore this for a moment. So we want to imagine that we have a cylindrical pipe in the sense of it has constant cross section, and the cross section we're going to denote by omega. And then we're going to imagine that water's flowing through this pipe, and the flow is laminar flow, so there's no turbulence. The water's incompressible, all these nice assumptions that we would normally make. Now, this kind of phenomenon is very, very well understood for the past couple of hundred years. And it's known that you want to consider what's known as the streamline function, which is a function from omega to r. And when you do that, the streamline function satisfies that its Laplacian is constant in omega. So well, if I choose units, then I can make the constant 1. So actually my streamline function satisfies minus Laplacian u is 1 in omega, and then it also satisfies u is 0 on the boundary, which is a no slip condition. So this is a very standard condition. So just to remind everyone, the delta refers to the Laplacian, which is the sum of pure second derivatives. Of course, this makes sense in higher dimensions, and actually this problem was addressed in higher dimensions, even though I was talking about 2 dimensions just now. Now we're going to do something strange, and we're also going to assume that u has constant Neumann derivative on the boundary. So in general, not every solution to this equation for any omega will also satisfy that it has constant Neumann derivative on the boundary. So mathematically, what this extra condition corresponds to is a Lagrange multiplier, which comes from the assumption of u maximizing a certain functional, which is called the torsional rigidity. So you can see how this is maybe related to maybe what an engineer might want. So the torsional rigidity somehow measures the pipe's well, rigidity against torsion. Okay, so we want to maximize this. We want the strongest pipe possible. Now, again, to emphasize, the goal, right, is to classify the regions where my solution so I have a solution to the PDE and I satisfy the overdetermined conditions. So the famous result is this result due to James Serrin, which was proved in 1971. So Serrin says, suppose that omega is a subset of Rn, it's a bounded domain and it has C2 boundary. Now, if there exists a solution that satisfies that U has constant Laplacian in omega, U is 0 on the boundary, so Dirichlet boundary conditions, and the normal derivative of U is constant on the boundary, so constant Neumann conditions, then omega must be a ball. Okay, so this is usually the goal of overdetermined problems. When we have a full overdetermined condition like this, we want to show that the region is a ball. Now, Serrin actually proved this in a more general case. So he considered a right-hand side that was semi-linear. And he also considered the case that the Laplacian was replaced by operators of mean value type. And then he still got the result that omega was a ball. Now, I should also mention, sorry, with a semi-linear case, he has to assume that U is non-negative. So we'll see this in a little bit. And actually, something quite fascinating is if you drop this assumption that U is non-negative in the semi-linear case, then the problem's open still. So it's a famous problem that suppose you have U satisfies the eigenvalue equation with 0 Dirichlet boundary conditions, constant Neumann boundary conditions, but no assumption on the sign, it's still open whether omega must be a ball. Now, anyways, so how did Serrin prove this? He used a powerful technique that is now known as the method of moving planes. So this method of moving planes was kind of originally introduced some years earlier by Alexandrov to prove the soap bubble theorem, which says that that if I have a set and its boundary has constant, a bounded set, I should say, and its boundary has constant mean curvature, then actually it's a ball. Okay, so Alexandrov introduced a reflection principle to prove this, and Serrin refined this to what's now known as the method of moving planes. Now, the method of moving planes has been used a ton all over PDEs. So it was famously applied by Gidas, Nirenberg, and Ni to prove symmetry of semi-linear solutions to semi-linear equations in a ball, also assuming that the solution had a sign. Now, overdetermined problems have also been considered in many different situations. So they've been considered on manifolds, for example, with fully nonlinear equations, other overdetermined conditions, and other operators, for example. Now, the problem we actually care about is going to generalize Serrin's problem in two ways. Namely, we're going to change the overdetermined conditions, and we're also going to change the operator. So first of all, what is the operator that we care about? So we care about the so-called fractional Laplacian. So as Daniel mentioned, the fractional Laplacian is incredibly popular to study in the literature at the moment. So in fact, it's been studied by the probability community for maybe about 50 to 100 years now. So about the beginning of last century. But it's received a lot of attention in the past 20 years, particularly after the famous paper of Caffarelli and Silvestre, where they proved the extension principle for this equation. So essentially, this operator, sorry. So essentially, you can understand this operator as a by extending into higher dimensions and thinking of it as a Dirichlet to Neumann map. Now, it's been receiving a lot of attention, particularly from the mathematical analysis community, and people are trying to understand the regularity of equations involving the fractional Laplacian and so on. So I should mention that we normally call the fractional Laplacian a non-local operator because of this integral over Rn, which means in order to define the fractional Laplacian of u, we need to actually know the value of u in all of Rn. And if we were to perturb u very, very far away, this has an effect on its fractional Laplacian at a given point. Okay, so what this non-locality translates to with the analysis is different maximum principles and Harnack inequalities. So often we need assumptions in all of Rn as opposed to just on a set of measure 0 on a surface, for example. So we'll see that a bit later. Now, why is it called the fractional Laplacian? Because of these two properties. So if we compose the fractional Laplacian with a fractional Laplacian of a different order, this corresponds to just adding the powers of the fractional Laplacian. And as we take s back up to 1, we recover the original Laplacian. So it's really a fractional analog of the minus Laplacian. Okay, so what is the overdetermined condition that we care about? So this is sort of the geometric context of our problem. We begin with a bounded domain G, and we consider omega as this set that we form from the Minkowski sum of G and a ball of radius r. So the Minkowski sum is defined in this way. And what it essentially corresponds to is the boundary of G is parallel to the boundary of omega. So the distance between the boundary of G and the boundary of omega is constant, and it's equal to this radius r of this given ball. So we have some regularity assumptions on G. So G is, of course, bounded and open, and it has C1 boundary. And we consider a function f from R to R that's locally Lipschitz. Again, omega is this Minkowski sum of G and a ball of radius R. And now we take a function that's non-negative and not identically 0 and assume that it satisfies this PDE. So we have that its fractional Laplacian is equal to f of u in omega. We have that u is 0 in the complement of omega. So this is Dirichlet boundary conditions in the non-local case. So in the local case, this assumption is u is 0 on the boundary. But in the non-local case, we have to do the complement. And we assume that u is constant on the boundary of G. So on this surface that's parallel to the boundary of omega, we have that u is some prescribed constant. Now, in this situation, we're able to prove that u is radially symmetric, u is strictly positive in omega, and omega and hence G is in fact a ball. Okay, so I should mention these assumptions on the regularity of u can be relaxed, but they're essentially there because this is what you need to define the fractional Laplacian pointwise, or at least sufficient to define the fractional Laplacian pointwise. So this problem was originally introduced in the local case, so when S is 1, by Ciraulo, Magnanini, and Sakaguchi. And they introduced it in the context of invariant isothermal surfaces of nonlinear, non-degenerate fast diffusion equations. They also introduced it as a generalization of Ceran's problem. So often this problem is called the discrete Ceran's problem, because if we think about this shape, and if we imagine we had an infinite number of these surfaces that u is a constant on, maybe different constants for each surface, then this is going to recover the constant Neumann condition in Seren's problem. So this is kind of like a discrete analog of Seren's problem, where we've just prescribed that u is constant on one parallel surface. Okay, so I should say Ciraulo, Magnanini, and Sakaguchi obtained this result. They had to assume that G was connected, which is essential in the local case. In the non-local case, it's not essential because, again, the non-local case sees mass far away. So it rules out, you don't need this assumption in the non-local case. And I should also mention that in the case that F is 1, again, in the non-local case, this problem was looked at by Ciraulo, Di Piero, Poggessi, Polastro, and Valdinoci in 2021. Okay, so what is the idea of the proof of this theorem? So the idea is to use this method of moving planes. So the method of moving planes begins by picking a direction E in the n-1 sphere. We have this parameter mu, and we have T mu, which is our plane. Okay, so I have a bit of a demonstration. So I should say we consider as well a function v mu, which is the solution u minus u evaluated at its reflection across the plane T mu. So let's so hopefully you guys should see my Chrome and Desmos. So please tell me if you can't see that. But anyway, so this is the idea. So we have some shape. So this is, for example, could be my omega. And we have this moving plane, and we translate our plane from right to left. And at some point, I start to intersect my region. And when I intersect, I take the right-hand side and I reflect it across to the left-hand side. And my v mu, which was my reflected version of my solution u, in this green patch is going to satisfy some PDE. And as I keep moving my plane from right to left, at some point, my reflected region wants to leave my original region. So if I keep going, then I jump out of my region. Now, what we care about is this critical point when I go as far as I physically can before I have to leave. And we call this the critical time. And essentially the idea is I want to prove that my v mu is 0 at this time, because then this means what this is going to correspond to is that omega is symmetric at this time. And because this was done for an arbitrary direction E, omega will have to be a ball. So geometrically, there are sort of two situations that can occur. There's this first situation here where I have I become internally tangent. So my reflected region intersects the boundary of my original region at some point. Now, the other situation that can occur is when I have an egg shape like this, in which case, at some point here, when I go further, I don't become internally tangent, but my reflected region kind of pushes out the sides. So these are the sort of only two cases that can occur geometrically when I run the method of moving planes. And so I have to consider these two cases separately in the proof. So so hopefully everyone can see my slides again. Okay. So yeah, so this is the goal, that we want to prove that this v mu is 0 at the critical time in both of these two geometric situations. So the first step of this whole process is that we want to prove that actually our v mu is non-negative. Now this h prime mu just refers to the half space on the left, so the left-hand side of the plane. This lowercase lambda is the critical time. The uppercase lambda is just the time that we hit our omega. So this one's not really so important, but the lowercase lambda is the important one, the critical time. So as I mentioned, our v mu satisfies a particular PDE, and the PDE is this one. So we have that v mu satisfies a linear equation with zeroth order terms. The zeroth order term comes from this f, the non-linearity. And we were able to define this C because f is locally Lipschitz. So this will be bounded, which will be useful to apply maximum principles later. Now, just to sort of briefly describe how we prove step one. So let's just consider the simplest case, which is when this C mu is 0. So that corresponds to, if f is constant, then C mu is 0. And in this case, our v mu is S harmonic in omega prime mu. So the omega prime mu was the right-hand side that got reflected across to the left-hand side. We also know that v mu is non-negative in the complement of the half space of this omega mu prime. Okay, now if this was the local case, this condition here would just be v mu is non-negative on the boundary of omega mu prime, and we can just immediately apply the maximum principle, just immediately. Now, we can't do this in the non-local case because the issue is the maximum principle for non-local operators requires v mu is non-negative in all of Rn, but the only anti-symmetric functions which are non-negative in all of Rn are the zero function. So this is a major issue in this case. So this problem was addressed in a famous paper of Fal and Jarosz. And in this paper, they actually looked at the original Ceran's problem, except for the fractional Laplacian. And in order to do that, they had to obtain all of these anti-symmetric maximum principles. So in this case, they showed that if omega is a subset of a half plane and it's open and bounded, V is S harmonic, V is non-negative in the half plane minus omega, and V is anti-symmetric, then in fact, V is non-negative in omega. So you really have to use anti-symmetry in order to get this result. Okay. So they also proved this in the case where there's a zeroth order term, but you need to be a little bit more careful. Just like in the local case, the maximum principle only holds with zeroth order terms when the L infinity norm of C mu is sufficiently small compared to say the first eigenvalue. So you have to be careful like this in the local case and in the non-local case. But anyway, so we obtained step one essentially using this proposition. Now, step two is to show that at the critical time, we actually have v mu is 0 in all of Rn. So to do this, we first use the strong maximum principle to say that either v lambda is 0 or it's strictly positive in the reflected region omega lambda prime. And for the sake of contradiction, we suppose that actually we're strictly positive. We're not 0. And then we consider our two geometric cases separately. So in the first case, we had this internal touching. And so we can pick this point, which is where my original boundary and my reflected boundary touch. So that's P, and I choose the point that's on the boundary of G, not the boundary of omega. So this point here where my mouse is. And now when I evaluate V lambda at this point, well, P is on partial G, so it's some constant, but also the reflection of P is also on partial G. So U at the reflection of P is also the same constant. So we've got constant minus the same constant, which is 0, which contradicts that V lambda is positive. So we get a contradiction in the first case. In the second case, I was in this situation, and in this situation, I have that my hyperplane is normal to the boundary of G and the boundary of omega at some point, which I call Q. Now, since U is constant on the boundary of G, we can check that the derivative in the direction of E at this point Q is 0. So V is not changing in the direction of E at Q. Now, how we obtain a contradiction is via this Hopf type lemma that we had to prove. So we showed that if U is anti-symmetric, so this is maybe bad notation. I probably should have called this V. But so if U is an anti-symmetric function and it is a super solution of this zeroth order equation, linear zeroth order equation, it's non-negative in the half plane and it's strictly positive in B1 plus, then actually the derivative across the half plane has to have a strict sign. So this is kind of analogous to the classical Hopf lemma where you show that the Neumann derivative on the boundary has to have a strict sign. Something to quickly mention here is that this can be a little bit surprising for some people who maybe know non-local equations, because the boundary regularity of non-local equations is very different to that of local equations. And normally you only expect solutions to non-local equations to be Holder continuous up to the boundary. So it doesn't really make sense to consider its Neumann derivative. But actually, the anti-symmetry saves us here because my function's anti-symmetric. In a sense, this derivative is not on the boundary of my B1 plus. It's not on the boundary of B1 plus. It's more of an interior result because I can reflect anti-symmetrically to the other side. And in the interior case, it does make sense to have a derivative like this for U. Okay, so this lemma gives as a contradiction to this, and this essentially proves the result. So the only thing is that to show that this assumption here actually implies that omega is a ball, but this follows from a result due to Veth, as Daniel was mentioning earlier. So this concludes the proof of this result. This shows that omega actually has to be a ball in the end. Okay, so what I've been talking about so far is essentially rigidity of this problem. So given an overdetermined condition, can I show that I'm a ball? In which case, we just showed that we can. Now, a topic that's looked at is being looked at a lot at the moment is the stability of this problem. So suppose that instead of having our well-posed PDE plus the overdetermined condition, I instead have my well-posed PDE, but I almost satisfy my overdetermined condition in some sense. Well, then, can I argue that my region is almost a ball? So under small perturbations of my overdetermined condition, can I show that I'm a small perturbation of a ball? Now, of course, whenever you do these kinds of results, you have to be careful by what you mean by almost. So in the context of our problem, how we measure u being close to being a constant on the boundary of G is via this Lipschitz semi-norm. So you can see that this term is going to be 0 if and only if u is constant on the boundary of G. And how we measure how close omega is to a ball is through this row of omega. So what we do is we pick a point P in omega, we take the largest possible ball inside omega, we take the smallest possible ball outside omega, both at the same point, and we look at the difference in their radii, and then rho of omega is the smallest possible difference that we can obtain. So in some sense, this is like an L infinity estimate on how close omega is to being a ball. Now, some literature on similar kinds of problems. So this kind of idea was first looked at by Aftalion, Buska, and Reichel in 1999 in the context of Seren's problem with the semi-linearity. And they showed the following inequality. So they have the same row of omega on the left-hand side, and they've got the Neumann derivative minus some constant in the C1 norm on the boundary of omega. And they have this log term to some power. Now, this all comes out from the fact that they have to be very careful because they're going close to the boundary. So it's really the boundary analysis that leads to this log and this -1 on n. Now, in the parallel surface problem, so in the local case, this was looked at by Ciraulo, Magnanini, and Sakaguchi. So this was a year after their original paper where they introduced the rigidity version of this problem. And they showed that actually rho of omega is controlled by some constant times by the Lipschitz norm. So this inequality, of course, is much nicer than the one up here. And essentially the reason for that is this boundary of G is compactly contained in omega. So really it's an interior result. We don't have to worry about going up to the boundary. Okay. Now, in the paper of Ciraulo, Di Piero, Pogesi, Polastro, and Valdinoci, where they did it in the non-local case with F is 1, they obtained a very similar result to Ciraulo, Magnanini, and Sakaguchi, except they had this power of 1 on S plus 2. So this power is not optimal in some sense. Like straight away, when we set S to be 1, we don't recover the linear power in the local case. So that's an issue. Now, essentially, this power comes from the fact that from the non-locality of the equation and the fact that the fractional Laplacian sees mass that's far away. So I'm going to discuss this in a little more detail in just a moment. But first, I want to mention the result that I obtained with Di Piero, Pogesi, and Valdinoci. So we considered this problem in the semi-linear case. So again, G is an open-bounded subset of Rn. Omega is this Minkowski sum of G in a ball. And we have some regularity assumptions on the boundary of omega. We also assume f of 0 is non-negative. So this is actually an assumption that appears in the other papers as well. And this is to get some maximum principles in the semi-linear case. And in this situation, we show the same inequality that was true in the case that f is 1 with the same power, this power 1 on s plus 2. Okay. Now, so okay. Yep, so sort of the final part of my talk, I just want to discuss this power. So really this is an open problem in this, well, it is an open problem in for the parallel surface problem. So under some reasonable assumptions on omega, what is the optimal alpha positive such that rho of omega is less than or equal to some constant times by the Lipschitz semi-norm of u on the boundary of G to the power alpha. Okay, so alpha, of course, from this result is bigger than or equal to 1 on s plus 2. Now, what should this alpha be? So since this is an interior result, and the regularity theory for fractional equations is in some sense similar to the linear, to the local case in the interior, we would expect that maybe we should recover the same inequality that we got in the local case, which is the power alpha equals 1. So this is sort of supported by this computation that we did, which we took g epsilon to be such that g epsilon plus 1/2 is an ellipse, okay, and it's only kind of elliptical in one direction. So it's kind of just like this. Now in this situation, rho of omega epsilon is explicit and it's just epsilon. And we can show through challenging but elementary computations that as epsilon goes to 0, the Lipschitz semi-norm of the solution u epsilon. So I should mention u epsilon satisfies the semi-linear equation when f is 1, so the solution to the torsion problem. And this is good because in this case, actually u epsilon is explicit for the non-local case and the local case, of course. So we can do the computation and show that this semi-norm behaves like epsilon as epsilon goes to 0. So this suggests that alpha is 1, just as in the local case. Now, the non-local case, as I mentioned, creates difficulties because the fractional Laplacian sees mass that's far away. So to kind of illustrate this, I wanted to give a bit of a computation. Now, again, I take f to be 1, just keep everything nice and simple. And I take this Lipschitz semi-norm to be small, which, because of our stability result with the suboptimal power, does mean that omega is uniformly close to some ball, which let's say it's just a ball of radius 1. Now, consider like a very specific geometric situation, which is the reflected region is precisely B1. So the right-hand side is B1, and it reflects to give that this total reflected region is just a ball. And so omega isn't quite the ball, right? So this is omega, this black line is omega here, but it's uniformly close to a ball. Okay. And the reason why I'm doing this is because we can explicitly solve, so that the assumption f equals 1 means that my reflected function v mu is S harmonic, like usual, like before, sorry. And in this case, we can actually explicitly solve for v mu using the Poisson kernel. So there's a Poisson representation formula for the non-local case as well as the local case. So when we solve for v mu at the critical time, and we use the fact that v mu is anti-symmetric, and we use the fact that u is 0 outside of omega, we obtain this explicit formula for v lambda. Okay, so v lambda is v mu except at the critical time lambda. Okay, so we have this expression, and from this expression we can use that omega is uniformly close to b1 to argue that G, our region on the inside, is compactly contained in B1. And we can use the regularity theory for the fractional Laplacian, which says that U here is bounded from below by distance to the S to the boundary. So delta to the partial A denotes distance to the boundary of A. And so here, this norm of y minus 1 to the s is the distance to the boundary of b1 to the s. So we essentially can obtain this inequality in this really specific geometric case. And this inequality is in some sense sharp in that the stuff that I've thrown away is all order 1 when the Lipschitz norm is close to 0. So I've only thrown away stuff that's kind of bounded away from 0 in order to get this inequality. And also it's indicative of the general case in that I've only really used the regularity theory for the fractional Laplacian, which holds for general regions. And I've used that the Poisson kernel has this, gets this delta to the S, which is from Poisson kernel estimates believable. So we obtain this inequality. Now, in order to prove the result, the optimal result, so when alpha is 1, we need to show that this term behaves like rho to the omega as the semi norm of u goes to 0. But this is requiring really precise estimates up to the boundary because, okay, point-wise, this distance goes to this distance, but we're dividing by something that's going to 0 at the boundary. And so to show that these two behave the same requires, fine estimates up to the boundary, which is really surprising because the result is really an interior result. It's not a boundary result, except it requires these estimates up to the boundary. And this is, like I mentioned before, because the fractional Laplacian sees this mass that's appearing. So I've said here that if you can show this, you're kind of done because I've chosen a very specific situation, but it's also quite representative of the general case. So if you can understand, if you can prove something like this, then you've got sort of most of what you need in order to get the full optimal result. But anyway, so this is still an open problem, and that's essentially everything that I had to say. So thank you very much for listening, and yeah, thank you very much.
Thank you, Jack. Thank you for this
Thank you.
very interesting talk and for showing your results. I guess this all goes into your PhD thesis. Are there any questions or remarks by the audience, by the attendees? Please raise your hand and I can give you access to speak. No question? Okay. So it's a very clear talk. I also have to confirm, like Professor Takahashi said, it was a very clear talk, very well explained, the moving plane method. It's really nice to see. So
yeah, it's I like the animation because it's very geometric. It's very nice. So
Professor Giga had a question. So if you want, you can speak. You have to unmute yourself.
Okay, thank you for your nice talk. I have a question. Could you show me the definition of rho? And is it possible to replace rho by other quantity to assume the similar assumption? Rho of omega.
Rho was here.
So it is okay. Many people use this quantity, but are there any other way to estimate the difference between Bohr and omega?
That's an excellent question. So yeah, yes and no. So this particular quantity is chosen because it actually works very, very nicely with the method of moving planes. So I can't think of any quantities off the top of my head that are independent of the choice of direction. So often estimates are obtained in one direction, and then you'll have something like the measure of the symmetric difference between omega and your reflected region. So estimates like that, but this is dependent on the direction you picked in the first place, and then you want to use your results to obtain something that's independent of the direction. And that I can think of, I can only think of this one, though I'm certain there will be other reasonable things to consider out there.
Okay, thank you very much. Yeah, at least it's consistent with moving plane method. Okay, thank you very much.
Thank you. Thank you.
Okay. Are there any questions or remarks? So if not, then let's thank the speaker again. And there is a coffee break where you can ask further questions to Jack, and you should all have received a reminder email. And in the bottom of this reminder email, there is a link which I will now post in the chat, which is exactly the coffee break link. 1 second, I will post it. So please join us in a few minutes. We will start straight after this now. I will close now the webinar, and then you are warmly welcome to ask further question to Jack. Okay. Thank you, everybody.
Thank you.
See you. Bye.